So let me introduce quickly Alex, who's going to talk to us about non-cooperative game theory for autonomous racing. Alexander has done his bachelor, master, and PhD at ETH Zurich. His PhD was at the Automatic Control Lab, and now he's a postdoctoral researcher at the Computer Vision Lab at ETH Zurich. It's has been working on model predictive control, viability theory, game theory applications to driving and racing, and now it's also exploring the field of computer vision and learning. Okay, Alex, thank you for joining, and looking forward to hear what you have to say.
Thanks for the kind introduction, and yes, I'm looking forward to speak to this interesting tutorial about the work I did. I mean, this was still during my PhD, where I did most of it on basically game theoretic motion planning for autonomous racing. So let's start with kind of a motivation and differentiation between autonomous driving and autonomous racing. So autonomous driving is a huge research area. It's active since the 1980s, and the research is done both in industry and academia. And the most successful companies are driving way more. For example, drove over 20 million miles autonomously on public roads by now. And kind of, for me, I would say that the really challenge for it is kind of taking safety critical decisions, especially when the environment is uncertain. So when you have other cars around you which behave in a hard to predict fashion. This is actually also a problem where game theoretic motion planning is a nice application to. But what I will talk to you today is kind of my work on autonomous racing. Autonomous racing is much less studied than autonomous driving. And really the goal there is to drive as fast as possible around the racetrack. So there's a very simple and clear definition of what the goal is. And for, over the years, kind of the experimental platforms changed a bit. At the beginning, I would say, most people did it using miniature race cars, as the work I will show you. And then more and more kind of full-scale competition showed up. So there is the Formula Student driverless competition, which I was always also involved in over the last years, where Zurich actually has very nice results as well. And then other competitions showed up, such as Robo Race, and then most recently, I would say, Indy Autonomous. Now, as a difference to autonomous driving, really in autonomous racing, we have a more structured environment. You have really one racetrack. There is no, there are no complicated road networks or things like that. But this environment is very competitive. So, cars try to overtake you, you try to block them, and so on. And to really succeed in autonomous racing, I think you need to solve kind of 3 challenges. The first one is you need to drive as fast as possible. If you're driving too slow, you will not win because someone will be faster. And kind of from a technical perspective, this translates to motion planning for highly nonlinear systems. There is actually a way to share sharing with optimized for videos, such that you can hopefully see nicely the videos I will show you. Okay, so the second challenge is kind of staying safe inside the track. If you crash, you will lose, as either your car is broken or you will slow down and another car can overtake you. And kind of from a technical side, this corresponds to somehow infinite horizon constraint satisfaction. Things I just before the break mentioned with recursive visibility. And then the last part, the thing I will talk about today, is kind of interaction with other cars. And this, from kind of a theoretical perspective, is kind of a decision-making problem in a highly dynamic, non-cooperative environment. So again, we basically have to solve 3 very challenging problems to get to something which works. Now, how to solve that, I kind of, during this work, I translated them in kind of 3 ingredients. The first one is we want to finish first. And this we approximate by maximizing the progress. So the progress is just the distance from the beginning of the racetrack until the end of our predicted trajectory. And this allows us to, kind of introduce a nice ordering into our trajectories. So for example, clearly the green trajectory is better than the yellow trajectory. Now, the second one is we don't want to collide, as this kind of, we want to finish. And the second one is also, again, related to constraints. We also want to stay inside the racetrack. Okay. Now, all of the things I will show you are really meant to work in conjunction with with the experimental setup I used at this time, which is the Orca setup hosted at IFA, at ETH. And it works as follows. We have an overhead camera system, which can track multiple cars. I think we can track up to 8 cars and get precise position and velocity of these cars. This information is then distributed to controller PCs. So we can have one controller PC for every car we want to control. And then the commands from the controller are sent to the real car via Bluetooth. And I hope in the video you can now see the car drive around the car. So, the cars drive, I would say, quite fast for their size. And, so kind of at least the driving as fast challenge seems to be solved. But now let's somehow take a step back and start really at the beginning of our motion planning framework. And for this, we need a model. The model we use is a dynamic bicycle model. So it's a bicycle model with nonlinear lateral tire forces, which we model with Pacheco magic formulas. So they define the lateral forces, so how the tires interact with the ground. And then finally, we also have a model of our drivetrain, which kind of models how the throttle we send to the car kind of actuates it, and then the steering angle. And all of that kind of defines how the velocities of our car change. And then given the velocities, we can integrate them and get out the position and orientation of the car. So what we end up with is a highly nonlinear 6-dimensional system. But the nice part is that we can kind of separate this dynamics into slow and fast dynamics. So we have the position, which change reasonably slow, at least compared to how fast the velocity change. And this separation we can now use to kind of build a motion planning framework. Now, this framework is meant for one car, but I will show you then later how to extend it to a multi-car setup. Okay, so the idea is to have a hierarchical structure where in the higher level, we do motion planning based on constant velocity primitives. So there we really plan for the slow dynamics. So the position and, the velocity is just considered as the motion primitives and as an abstract state. And what this allows us to basically reduce the dimensions. So we can run in 4 dimensions, somehow like the free position and then this abstract kind of constant velocity state instead of the 6 we had before. And I would say even more important, we can have much longer actuation time. So we don't need to decide what to do every 20 milliseconds, but now kind of every 0.16 seconds, for example. This turned out to be a good time for the system here. And if you would scale this up to a real car, this would be even much longer. So what are we now doing? Kind of with our motion primitives, we can do a recursive motion planning approach where we kind of build a tree of trajectories. So we use 129 motion primitive with a branching factor of around 15, depending exactly on the exact constant velocity. But yeah, roughly 15 is the branching factor. So at each point, you roughly branch 15 new trajectories out. And then we do this for 3 steps, which results in a complete look ahead of roughly half a second. We remove all the trajectory which leave the track, and what we end up is kind of the set of trajectories I showed you here. Out of these, we then pick the one which maximizes the progress. You can still remember from the ingredients slide, which would be this red trajectory. And then, given this red trajectory, we use a model predictive controller with the full dynamic bicycle model to track this path. And this allows us to kind of, plan in the slow dynamics, and then, the fast dynamics is taken care of by the MPC. However, you can kind of, if you look at these trajectories, you can see kind of an issue. A lot of them seem to crash into the wall. They don't crash yet into the wall, but within this kind of half a second look ahead, they just end up before the wall. Now, you should never pick such a trajectory, but unfortunately, with with our maximum progress objective, it actually happens more often than you think that you choose a trajectory which quite instantly, just after the end of the prediction horizon, will crash into a wall. So what we did is kind of investigated on how we can only generate safe trajectories. And we did this using viability theory. So we computed the viability kernel, which gives us basically a safe set. So all the kind of safe states around the track. And then we only generated trajectories which remained in the viability kernel, which kind of what you then end up with is the trajectory set on the left. Now, at the same point, we found some kind of ways to even, we also looked at the game theoretic viability kernel, which helped to take care of some of the approximation we did in the computation and gave us additional guarantees. And if you use this discriminating kernel, this game theoretic one, you end up with a bit more conservative set of safe trajectories on the left. Now, to basically maybe give you some impression on how this motion planner at least works for one car, I have some simulation results. And the nice part is that, or kind of the thing I wanted to highlight here is that the two kind of pruning strategies, so if you use discriminating kernel or the viability kernel as a safe set, changes the driving style quite in an interesting fashion. So if you use the viability, you get a more aggressive driver, and if you use the discriminating kernel, you get a more kind of a cautious driver which brakes early. But then, because it brakes early, it achieves higher speeds through the curve and can accelerate earlier. And what we end up with is that the two methods basically have the same lap time. Now, so this is really important for the later work, as it makes for interesting racing where different controllers have different driving styles, resulting in then different racing between cars. And just to highlight, if you don't use any of these kind of viability kernels, it still works, but actually the lap times are slower. And because you generate way more trajectories, you also spend much more computation time, or the computation time becomes much higher. So some nice side effect of proving safety. So given this kind of single agent motion planner, let's now think how we can merge it into a multi-agent game theoretic planner. And the idea is really to look at it from a trajectories perspective. So what we do is basically every trajectory, so every of these roughly 1,000 trajectories we generate, we consider to be an action. So each trajectory gets its own payoff, and then each, this payoff does not only depend on its own decision, but also on the decision of the other cars. Okay. Since since explaining you how this works with 1,000 trajectories will be very cumbersome, I decided to reduce it a bit and go with 3 trajectories. So the setup is kind of easy because we abstracted it to the trajectory. We get kind of to the bimatrix formulation, so the matrix game. Note that it kind of, because the trajectories are still built in a kind of a tree fashion, you could write it down in in the expensive form and do a lot of other things. But we decided to kind of extract everything away and transform the extensive form directly to a bimatrix game and do then the computation in the bimatrix. Not sure that this is the perfect decision, but it resulted in some nice results and it worked well for us. Okay, so now let me explain it. So given that each car has 3 trajectories, you end up with kind of payoff matrices of 3 by 3, where, for example, if both cars choose their green trajectory, the red car gets a payoff of A11, and then the yellow car gets a payoff of B11. And similar, you can do the combination for all the trajectories. And before I continue, kind of some definitions. The leader is always the car which is ahead at the beginning of at the beginning of this small game instance. Since we will solve this in a receding horizon fashion, who is the leader will actually change dynamically over the whole race, but at least for one game, it's always the one which is ahead at the beginning. So in this case, it would be the red. And then kind of, just because I will use this later, I consider a trajectory pair to be feasible if both trajectories stay inside the track and they do not collide. So the natural definition of a kind of a feasible trajectory. Good. So let's go to the actual part, and this is how do we model the game of racing? And for this, I propose kind of 3 different games. The first one is the sequential game, where we really exploit the leader-follower structure of racing. So kind of the guy ahead is the leader and the one in the back is the follower. And it works as follows. If a trajectory leaves the racetrack, the agent gets a very low payoff. In this case, -10. As long as it's negative, it's fine because the progress is always positive. And now, kind of for the leader will get a payoff depending on its progress, as long as it stays inside the track. And then the follower is a bit different. The follower still gets the payoff depending on the progress, but really how I computed here the progress is just use the definition of the progress and scaled everything such that the car is 12 centimeters long, which is the size of the car in the experimental setup. So this is how I came up with these magical numbers. But yes, let's go now to the follower, the yellow car. The yellow car also receives its payoff, with the exception if there is a collision. So if both choose the blue trajectory, the yellow car would receive a payoff of -1. Good. Now let's move to the slightly more interesting game, or actually the more interesting game is what I call the cooperative game. And it's cooperative not because we use cooperative game theory, but because both agents are considering collision avoidance. So in this game, also the red car receives a payoff of -1 if the trajectories collide. Good. But you may think, but this doesn't really capture racing where you want to stay ahead. And I completely agree. That's why the last game is kind of the blocking game, where we really try to add as much knowledge from racing into the payoff. And how it works, it kind of uses the same structure as the cooperative game with a small caveat. So similar to the cooperative game, if you leave the track, you get a -10 payoff. If you cause a collision, anyway, you get a payoff of -1. I mean, as long as it's smaller than 0, it's fine. And now comes kind of the caveat. So let's assume that the red car is playing its red trajectory, and then the yellow car kind of has 2 other trajectories it can take, the gray or the green one. And now the payoff is not just the progress, but but additionally there is a second payoff depending on the fact which trajectory is ahead at the end of the horizon. So if the yellow car chooses the gray trajectory, the yellow car is ahead at the end of the horizon. So no, sorry. If the yellow car chooses the gray trajectory, the red car stays ahead at the end of the horizon. So it receives the additional payoff. On the other hand, if the yellow car chooses the green trajectory, it overtakes it, and so the yellow car receives the additional payoff. And similarly, you can build up the rest of the Bay matrix game. So I think you already should know how to choose the trajectory. It will be game theory. And so here I really look into pure strategies. And I call an equilibrium trajectory pair basically A star and J star. And for this work, we have two equilibrium types which we are interested in. The first is the Stackelberg equilibrium, where you have this, again, a leader-follower structure, and the leader can enforce his trajectory or his action on the follower, and the follower plays best response. So in this case, for the leader, what he wants to do is kind of maximizing his payoff given the knowledge that the follower will play best response. And then the follower just plays best response. So it's really kind of a sequential thing. And then the other one is the classical Nash equilibrium, where none of the player benefits from unilaterally changing the trajectory. Okay, so how does this look if we apply these equilibrium concept to our games? So let's start with the sequential game. And I have to be honest, it's not really a game, because the decision of the leader of the red car do not depend on the decision of the other car. So whatever the yellow car is doing, it doesn't influence the decision of the follower. So we can use a sequential maximization approach where the red car just does what is best. In this case, it would be going straight and picking the blue trajectory. And then the follower just kind of plays a best response, which would be the green trajectory. Now, what's interesting is that this trajectory pair is also a Stackelberg equilibrium and even a Nash equilibrium of the more complicated cooperative game. I mean, you can easily see that it's a Nash equilibrium, for example, because neither the blue agent, neither the red agent would like to deviate, as otherwise it could only get 0.83 or -10. And for the blue agent, for the yellow agent, it would also not benefit. Now, there is an interesting kind of addition to the Nash equilibrium, and there is actually a second one, where kind of the opposite happens, where the leader avoids the best trajectory of the follower. And if you would look at more complicated games, there would be even way more Nash equilibrium. Okay, so this kind of allows us to kind of get this interesting theoretical point. So if the sequential game is feasible, so if this sequential maximization approach is feasible, then this is also an equilibrium of the cooperative game. However, and this really shows kind of the link to, this gives a nice link to what most people do in motion planning, where they predict the behavior of the other cars and then plan according to these trajectories. And kind of in this limited or in this kind of theoretical boundaries of what we look from discrete decisions and so on, this kind of idea, this first predict and then plan, corresponds to a Nash equilibrium of even a more complex game. Good. Now, there is a second theoretic caveat, and this is somehow the limitation of the sequential game. So in the cooperative game, we can prove that if there exists a feasible solution, this feasible solution will be chosen either by the Nash or the Stackelberg equilibrium. But on the other hand, if the sequential maximization is not feasible, then the sequential game will not have a feasible solution. Okay. Now, Before I move to the blocking game, let me maybe explain what I mean with blocking trajectories. So if we would do what we did before, let's say the sequential maximization approach, the red car would choose its blue trajectory, and then the yellow car could overtake it. Now, what the red car could do is kind of choose the green one and force the yellow car to avoid it and take a long route, which allows the red car to stay ahead. And basically how this works is that he threatens it by a collision. Okay, so see, now the question is, can we recover this kind of blocking behavior in the blocking game? And yes, if we use Stackelberg equilibrium. So basically theoretically said, if there exists a trajectory pair which is kind of a blocking trajectory pair, and the stay ahead reward payoff is high enough, the Stackelberg equilibrium will pick this. Now, the Nash equilibrium, on the other hand, will always be the same as the one of the cooperative game. And in other words, unless for kind of very weird conditions, the Nash equilibrium will be not a blocking trajectory, at least in this formulation here. Okay, so in summary, Stackelberg seems to be a better option for our case. We don't have problems with multiple Nash equilibrium and things like that. And given this, so all the analysis I will do all the simulations will use the Stackelberg equilibrium, which is also computationally nicer. And so we did a simulation study where we run the controller in closed loop and used these two drivers. And what you can see is that the cooperative game has by far the most overtaking maneuvers. Now, what's kind of special is that the sequential game has very little. And then the blocking game is somehow in between. So let me explain why the sequential game is so good at avoiding overtaking maneuvers. And the idea is really that in the sequential game, if the other car tries to overtake you, you will just ignore the other car and keep on driving on your ideal line. Now, any overtaking maneuver needs some cooperative part, or better, the fact that you don't want to crash. This is not given in the sequential game, but it's actually there in the cooperative and in the blocking game. And this is kind of how you avoid overtaking maneuvers in the sequential game. So here is also a simulation result where the red car just keeps on driving, even though the blue car tries to avoid to overtake it. Now, at some point, it's kind of too late for the blue car to react to this, and the simulation will go into an emergency braking maneuver. But even like this, the collision cannot be avoided. But what the red car achieves is it achieves to avoid the overtaking maneuver. In the cooperative game, this is not the case, and actually the red car gives enough space to the blue car to not collide, but at the same time this allows the overtaking maneuver. So now let's look at actually the difference between the cooperative game and the blocking game, which are the two interesting ones. So you can see now the start, and we now enter the first interesting overtaking region. And here what happens is that the cars really nicely mimic each other. And please remember how they look, because later you will see that this is not how they would normally drive. And okay, now comes again a quite boring part of the track, and we approach the second overtaking spot. Now here, the red car in both cases gets overtaken. But you can see that in the blocking game, the red car tried, at least in my opinion, harder to not get overtaken. Okay, so now the cars go back and enter again our other overtaking spot. And in this case, in the blocking game, the blue car is able to stay ahead, whereas in the other game, the red car can actually pass at this point. And you can also see how different the trajectories are, which shows kind of the mimicking happened in the first lap. Okay, so now to find a kind of to finish, I want to kind of show you some real-time physical implementations. But for this, we had to solve some challenges. So kind of the problem is that solving or building the bimatrix game becomes extremely challenging from a computational side, as the entries in the matrix grow quadratically. And mainly the collision checks become an issue, as if you have 1,000 trajectories each, this means 1,000,000 trajectories, which you have to check. And if you use even a reasonable kind of discretization time for the collision checks, this ends up with 32 million collision checks. And this you can just not do in 20 milliseconds, which is the time required to run it on the real-time system. So what we did is kind of simple and heuristic. We reduced the prediction horizon to 2, which drastically reduces the number of trajectories. And then we used a kind of a beam search style solution. So we only kept the 60 best trajectories in terms of progress, and only for those we were building the bimatrix game. Now, by cutting the prediction horizon so much, you lose all the kind of nice properties of predictive controllers. So we had to somehow regain a bit. And we did this by using kind of an approximate future progress, or in other words, a value function. So we gave each trajectory, again, an approximate, what is somehow the approximate progress it will do from this state in the next in the next half a second. Okay, and this, with this modification, we were then able to kind of implement this. And yeah, I think, so you can see here now the cars driving against each other, overtaking, blocking, mimicking. It's not perfect. Sometimes you have collisions with the walls. Sometimes you have a bit collision with with each other. But I think it's still very fascinating to look the cars drive around. Okay, so with this, I think it's time to end. And what I showed is, or better, I showed you kind of complete autonomous racing pipeline, where we had different behaviors, both from the kind of viability kernel we used, but also from the game we used. We also got some interesting insights into kind of the non-corporate decision making. And I think the thing, for me, the biggest takeaway is that doing sequential methods works well most of the time, but it fails exactly at the point where you don't want it to fail. So where you have the most interaction, these methods will fail. And then kind of in future work, one thing is kind of making the real-time implementation more reliable. So, potentially consider the uncertainty such that cars are not going that close, using kind of more sophisticated ways to learn the terminal value function. And finally, implement it on a GPU. At the moment, this is implemented on a CPU from, I think, 2013. So yeah. And then other ways to improve would be kind of do model learning for the MPC, which could make the driving just a bit better. And then the last work, which is maybe a bit of a different direction, but something I'm currently working on and I'm quite excited about, is kind of figuring out how we can learn how the opponent behaves directly from large-scale data sets. And this can be especially important not for autonomous racing, but for urban driving, where behaviors are much more diverse. Okay, thanks a lot, and I'm open to questions.
Thank you, Alex. Thank you for the great talk. Do you have access to the document, to the Google Doc? So I think there were. So let's start from the.
I have. I just found out that I have another laptop next to me.
It's fine. I can.
But yeah, you can also read them to me.
I'll repeat them also for the recordings. So the first question is about, let's say, your experimental setup, and they're asking what's the approximate delays in the entire loop. Here, they are asking that they assume it's significant in the Bluetooth part.
It is significant. So as I said, the computation time is about 20 milliseconds, and the delay is roughly between 30 and 40 milliseconds. So this includes kind of what we did is we did a simple delay experiment. So we toggled an LED on the car. So no, we sent a command to toggle an LED on the car, and then we recorded how long does it take until kind of the controller PCs receives the information that this LED was toggled. So it's quite significant, and you need to have sophisticated delay compensation methods. So we use a special Kalman filter for delay compensation in here. If you want to know more, I think I described quite a bit of these details in my PhD thesis, which is publicly available on the ETH server.
Okay, thank you. Did you take any special, let's say, workaround in the multi-agent setting to deal with this?
No, actually not. I mean, one thing which made it harder is that I don't know the exact inputs the other cars used. There were kind of some approximate methods to kind of guess what is the low-level input sent to the cars to do these computations. So this added a bit of complexity, but otherwise, no, it was basically the standard approach.
Okay. So the second question regards the cooperative game formulation, if you can clarify it a bit, because here they are asking whether it's actually a cooperative game.
No, I mean,
okay.
it's a non-zero sum by matrix game, and we solve for the solution we at the end take is the Stackelberg equilibrium or the non-cooperative game. So really, what we wanted to highlight with cooperative is that both cars care about collision avoidance. So the moment basically the cooperativeness comes in, the moment the sequential maximization is not feasible anymore, game theoretic planning gives you, even if you solve for a non-cooperative solution, which means that the decision process is not, basically non-cooperative in the sense that I can run this on two PCs and both PCs will end up with the same solution. So I don't need any communication between the PCs. I can use kind of Nash or Stackelberg equilibrium, and in that sense, it's non-cooperative. But the behavior I get out of it is cooperative. So both cars try to avoid a collision. So if one of them maneuvers itself into a situation where it cannot avoid the collision, then the other car will basically help avoid the collision. This is really what I wanted to show with the difference between the sequential game and the cooperative game. And this is also what I kind of like the most out of these game theoretic motion planners, as we can get these very elaborate behaviors out of them.
Thank you. I see. Then there's another question saying, can you apply your optimization algorithm on a MBD vehicle model? Is your solution working for real-time simulation? So here I'm not 100% sure by what they mean by MBD, to be honest.
Me neither, to be completely honest. So
if
yeah,
the
whole thing starts to be real time once you take all the kind of tricks I used for the real time implementation. So really, to make this stuff real time, you need to use quite a lot of tricks. I mean, maybe the best thing to do would run it on a GPU, which we did it once for the single agent case, and there it gave us make a speed up, I think, of a factor of 60 or 70 compared to a CPU. So yeah, running that stuff on a GPU would definitely help a lot. But as it is, at the moment, real time is really one of the big issues.
Okay. So then there's another question asking, when the follower car crashes into the leader car, as in the sequential game setup, is the follower not being rational? Shouldn't the follower always avoid a collision, or is it the same? There's some noise.
Exactly. The problem is kind of recursive feasibility. So at the moment the car decided to dive in and try to overtake, everything looked fine. And this decision was kind of better than staying behind. Now, the problem is that this decision neglected that then in the future, once both cars move further, kind of this decision went to lead to a collision. So really the problem is kind of what kind of prediction horizon do you need to, I mean, either you need kind of theory, or the other way is you need extremely long prediction horizons. So yeah, this is kind of the issue. The one you base the controller decides to overtake at the point where, you know, just because that's how finite horizon planners work. You can take two kind of, you know, in the finite horizon, it's the right thing to do, but in the infinite horizon, it's actually the wrong thing to do.
Okay.
And then after that, the follower cannot avoid the collision by itself anymore. Just imagine kind of, you know, that this is what I try to show with this example here. You know, once, I mean, also in Formula One, once a car starts to do an overtaking maneuver, you know, the other car needs to cooperate with it. And, you know, if the leader car would just close the door, nevertheless, what the other car is doing, you know, it would result in a collision. That's basically somehow the issue. Okay, I hope this explained it a bit. It's
yeah. So I think in the meantime, we had a clarification on the MBD vehicle model, which stands for multi-body dynamics. So I think it was already kind of answered by you.
I mean, you know, none of the optimization stuff uses a multi-body dynamics model. So, you know, you would just use it for simulation. So it doesn't really change anything. And at the end, you would only, if you would use a more complicated model, you would use it in the MPC. And there, actually, I kind of have some works where we show that you can use much more complicated models than the one I used in the MPC. This is work with Tommaso Novi. I don't know if he's actually joining. He's also maybe joining the workshop. So yeah.
Okay.
Alessandro, without breaking the flows of questions too much, I have a quick follow-up question on the question about crashes, right?
Mm-hmm.
So if you look at the very last video you showed at the very end, there were a couple of maneuvers that are not allowed in Formula One,
Yeah.
like, you know, making the follower crash on the wall so that it doesn't pass. That's, you know, at least in theory, that would be something you can encode, right? If you have rules for the game, like, at least if you're able to tell, given the trajectories, whether they are legal or not,
yeah,
you could also add that.
I mean, I thought about this quite a bit, and you end up with some issues. So let's say you kind of need history to do it. So let's assume, okay, in Formula One, you're only allowed to change your you are only to do one defensive move. So I can kind of encode that in my future trajectory, I only want to do one defensive move. But now, if I play the game in a receding horizon fashion, I did the first move already. And if I don't consider this in my state or my history, then I don't know that I already did a defensive move, and I'm actually allowed to do one more. I'm just, you know, in my prediction horizon, I'm only allowed to do one, but you kind of need to keep track of what you did to enforce these rules.
Okay, thanks. That's a very nice example of multi-stage game which doesn't have a state which is completely Markovian. Okay, good, thanks.
All right, then where were we? In the future work part is mentioned model learning for MPC using Gaussian processes.
Yes.
Would a black box model learning algorithm, example given Cindy, be a plausible approach?
I mean, I don't know exactly, Cindy. I know my work we did on model learning for MPC. And there we actually used this kind of mix between physical dynamics and then learning kind of a correction term with machine learning tools. And this worked extremely well. So basically, this is not related to Gaussian processes. We did it with Gaussian processes, but since then I also looked at it from using some multi-layer perceptrons and things like this. And that all works nicely. Using kind of a black box tool, in my opinion, is kind of, I tried it once and it failed completely. Basically, the problem is that because you use an optimizer and a very, very strong optimizer in nonlinear model predictive control, it kind of can go and exploit any error in your model. So if there is kind of a weird combination of inputs which would allow to drive the car with 3 times the velocity, the optimizer most probably will find it. And then, you need to be extremely careful to kind of you get very limited amount of data. I mean, you can potentially get a lot of data, but all the data kind of is, in your, let's say, if you think about your 6-dimensional space for your vehicle dynamics model, it's all, the data you get is not distributed all over the whole state space, but it's really distributed in very narrow regions in this state space. So once you leave the kind of data support, your model is completely off. So this is something you need to be careful of. I don't know about Sandy, but yeah. I mean, if you're interested on what we did, there is a paper on learning-based model predictive control for autonomous racing, which you also apply to, I mean, actually the small cars here, and then also a Formula student car.
Okay, thank you. And the last question is, how is it possible to increase the number of agents in your experiment or increase the number of trajectories? For instance, a swarm of drones.
So let's say at the moment, there is kind of this fundamental leader-follower structure. So this would allow you to get kind of, you could kind of try to do it sequentially. So, you first play the game between the first 2 cars and then the next 2 cars and the next 2 cars. Like this, you get something which at least scales as it, the decision grow linearly. Theoretically, you could, of course, throw in everything into kind of, try to, I don't know. I mean, if you maybe use different tools than biometrics games, maybe some variational tools and things like that. But yeah, the method I was thinking about when I thought about it is kind of a sequential approach, as this would scale better than others. But yes, the decisions are not necessarily optimal. And I know people which did actually similar things for swarms of drones. They did kind of a sequential decision making, and then, kind of took game theory to abstract away some of the uncertainties. This is work by Claire Tomlin's group. But yeah, it's not, my method is very much not easy to extend to, I already run into computational issues with the setup, with what I showed here. Extending it to more complicated stuff will be computationally at least very hard.
Okay, thank you very much, Alex, for your talk.
Thanks again for giving me the opportunity to talk at this tutorial, and yeah, also teaching the people about this very interesting topic.